let's think back February 7th, 2000. If you are anywhere near tech or finance, then you probably remember the chaos.
Oh yeah, total panic. You had these massive websites, Yahoo, Amazon, eBay, CNN, just grind into a halt, completely overwhelmed.
It was huge, and everyone immediately thought, right, this has got to be sophisticated hackers, maybe state-sponsored. You know,
That was the assumption. I mean, companies with top-notch security suddenly just down looked like a massive coordinated attack. They were throwing around terms like 10 billion ghosts.
exactly. But the reality when it finally came out was almost more shocking. It completely reframed how we thought about network vulnerability.
It wasn't some shadowy group at all. No,
It was a 15-year-old kid in Montreal nicknamed Mafia Boy.
right? And he hadn't invented some crazy new exploit. He just hijacked hundreds of regular computers,
Yeah,
turned them into zombies, as you put it.
so it wasn't about genius code breaking. It was about using the network's own structure against itself, leveraging this inherent flaw in how everything was connected.
And that incident really, it's the perfect launchpad for our deep dive today into network science.
Okay,
Because this field, it's just exploded. It's showing us that all these complex systems, the web, yeah, but also supply chains, even the molecules inside our cells that follow these universal laws, surprisingly simple ones, actually.
so the goal is to understand the hidden architecture, the strict architecture, as our source calls it, behind all this complexity.
Precisely how can one teenager cause that much disruption? It's in the network structure.
So our mission today is to kind of fast-track that understanding. We need to move past some outdated ideas about randomness and networks,
Yeah, the old models.
right? And get to grips with how things are really linked and, crucially, what that means for, everything. Vulnerability, how viruses spread, how information travels. It's fundamental.
Absolutely.
Now, to really get this new network thinking, we actually need to rewind way back before computers.
Back to 1736.
The seven bridges problem. I remember this from a math class somewhere.
Yeah, it pops up. So the great mathematician Leonhard Euler gets this puzzle. Can you walk through the city, cross each of its seven bridges, but only cross each one once?
And he didn't just try walking it.
No, that's the genius. He simplified it. He said, look, the land areas, those are just points, nodes, the bridges connecting them. Those are lines, links.
He made a map, essentially an abstract one.
Exactly. And using that simple node and link map, he proved mathematically, nope, impossible. The specific way it was connected didn't allow for that path.
In that simple act, ignoring the geography, focusing on the connections. That's basically the birth certificate of graph theory of network thinking.
It laid the foundation. Now we can map anything that way. Friendships, roads, websites.
Okay, fast forward a few centuries, that idea of connections bursts into popular culture. 6 degrees of separation.
Right? Everyone knows the phrase.
But what's interesting is the idea itself is way older than the famous experiment.
Oh yeah,
Yeah, a Hungarian writer, Frigyes Karinthi. Back in 1929, he basically suggested everyone's connected by 5 people, max,
1929. Wow. Okay. And then came Stanley Milgram in the 60s.
right? The famous letter forwarding experiment. His results suggested what about 5.5 links on average?
That's the number everyone quotes. But here's a key point our sources highlight. Milgram's number probably overestimated the real distance.
Overestimated, but it's so famous. Why would it be too high? What was wrong with the experiment?
Well, think about it. The people in the chain, they didn't have a map of everyone. They had to guess. They'd send a letter to someone they thought might be closer based on job or location, you know? Oh, he's a doctor in Boston. My cousin lives near Boston.
But maybe their accountant's brother actually plays golf with the target. They just didn't know it.
Exactly. They lacked the global view, so their paths weren't the most efficient. The actual shortest path, if you knew all the links, is likely shorter, maybe less than 5.
The world is even smaller than we thought.
Seems that way. And now think about the web. Billions of pages seems vast.
Yeah, infinite almost.
But measurements showed on average, any 2 pages are only about 19 clicks apart.
19 clicks? That's nothing, relatively speaking.
It's another small world, hugely interconnected.
Okay, so things are tightly linked. The world is small. So the logical assumption, the one that kind of dominated math for a long time, was that these links must be random, right?
That was the dominant theory. Paul Erdos and Alfred Rennie, 1959, their random network model became the standard.
And what did that model predict? What would a random network look like? It predicted a very democratic system. Most things, people, websites, whatever the nodes are, would have roughly the same number of connections.
So if you plotted it out, you'd get that classic bell curve shape.
Exactly peaked in the middle around the average number of lengths. Very few outliers with tons of connections. Very few with almost none. Everybody sort of averaged.
Like height. Most people are around average height. You don't get many 7-footers, and you definitely don't get 50-footers.
Perfect analogy. The bell curve mathematically forbids those extreme outliers.
But wait, that just doesn't feel right for real life, does it? How so? Well, think about social networks. You've got some people with millions of followers and others with, 10. Or think about cities. Some are massive hubs, others are tiny towns. It's not averaged out at all.
You've hit the nail on the head. Yeah, that's the conflict. Real-world networks, social, biological, technological, they just didn't look like the random model predicted. They're way more clustered, way more, well, uneven.
The random theory was too simple or just wrong.
It was elegant mathematics, but it was fundamentally wrong about the architecture. It just couldn't explain the complexity we actually observe. We needed a new approach.
And that new approach, the big discovery, came from mapping the web, right? Barabási group in '99.
Yes, that was the turning point. They mapped out a huge chunk of the World Wide Web looking at how pages link to each other, and the structure they found was absolutely not random.
So no bell curve.
No bell curve at all. What they found was something called a power law.
Okay, power law for those of us who haven't brushed up on stats lately. What does that mean? How is it different from the bell curve?
Okay, think back to the height example, friend. The bell curve extremes are basically impossible. A power law is more like the distribution of, say, city populations or wealth.
Okay. Where you do get extremes, you get New York City, and you get tiny villages. You get billionaires and people with nothing.
Precisely. The power law curve decays much, much more slowly than a bill curve it allows for. In fact, it predicts the existence of these rare events, these nodes with a gigantic number of connections. The outliers aren't just possible, they're an inherent feature of the system.
The extremes kind of define the landscape.
You could say that. And what was truly mind-blowing was this power law wasn't just on the web.
Where else did they find it?
Everywhere they looked, networks of actors co-starring in movies, scientists citing each other's papers. Even the network of metabolic reactions happening inside a living cell, same pattern.
Whoa, okay, that's wild. From Hollywood actors to cell chemistry,
It suggested universal underlying principle.
is there a good way to visualize the difference between random and this power law network?
Yeah, the infrastructure analogy works really well. Think of a road map of the U.S. that's kind of like a random network. Most cities, big or small, have a similar number of major roads connecting to them. Pretty uniform.
Okay, got it. Lots of connections everywhere.
Now contrast that with an airline route map,
Okay, totally different picture.
right? You've got tons of small airports with maybe just a couple of routes, but then you have these massive hubs, Chicago, O'Hare, Atlanta, Dallas, that have hundreds of connections. They dominate the whole system.
That's a scale-free network.
Exactly. It's called scale-free because there's no single typical scale for a node. You don't have an average airport size that represents the whole system.
You just have this continuous range from the tiny ones up to the giants.
A continuous hierarchy. And that structure, those hubs, they aren't just there by chance.
So, how do they form? What makes networks organized this way?
It comes down to two really simple rules. Two mechanisms that seem to govern how most real-world networks evolve.
Okay, what are they? First, networks grow. They aren't static. New nodes, new websites, new people, new companies are constantly being added.
Makes sense. The internet's always getting bigger. Second, and this is the crucial part, preferential attachment.
The preferential attachment sounds like things like to connect to popular things.
That's exactly it. The rich get richer effect when a new node joins the network. It's much more likely to link to nodes that already have a lot of links.
It's like in high school, the new kid wants to be friends with the most popular kids, not the loners.
Or think about websites. When you create a new web page, are you more likely to link to Google or to some tiny personal blog nobody's ever heard of?
Google, obviously, or Wikipedia, the big hubs.
Right? And that simple preference repeated over and over as the network grows automatically generates that power law distribution. It naturally creates the hubs.
It's kind of like that catch-22 in Hollywood. You hear about you need good roles to get famous, but you need to be famous to get the good roles.
That's a perfect analogy. Success breeds success. Connectivity attracts more connectivity. It's a self-reinforcing loop.
And the simple mechanism explains why we see hubs everywhere, from social media giants to critical proteins in our cells.
It seems to be a fundamental organizing principle, and understanding this scale-free architecture, this hub structure reveals this really fascinating paradox about how these networks perform.
A paradox. Okay, what's the contradiction?
It's about resilience versus vulnerability. Scale-free networks are, on the one hand, incredibly robust against random failures.
We're must-how.
Well, think about the airline map again. Most nodes are small airports. If you randomly shut down a bunch of those small airports due to, say, bad weather across the region,
it's annoying for the people there. But the national air travel system as a whole isn't really crippled.
Exactly because most nodes are small, random hits are overwhelmingly likely to affect those small, less important nodes. The network connectivity largely holds up. It can absorb a lot of random damage.
Okay, so that's the robust part. What's the flip side?
The flip side is extreme fragility to targeted attacks.
Because of the hubs.
Precisely. Those few highly connected hubs are the glue holding the entire network together. If you deliberately take out just a few of those key hubs,
like Chicago O'Hare,
the entire network can shatter. It breaks apart into disconnected islands. Very quickly, the system collapses.
So robust to accidents, but incredibly vulnerable to deliberate targeting. That's the Achilles heel.
That's a paradox, and it brings us right back to Mafia Boy.
Right? He didn't hit random computers. He went after the big ones.
He went after the servers for Yahoo, for CNN. He targeted the hubs responsible for delivering the service. He didn't need to take down the whole internet. He just needed to cripple those central points, and the effect was massive because of their position in the network.
That makes so much sense now. The structure itself created the vulnerability he exploited.
Exactly. And this hub structure doesn't just affect robustness, it completely changes how things spread through the network.
Things like computer viruses or even ideas and fads.
Everything. The old models, the ones based on random networks, predicted something called a critical threshold.
Meaning what? A tipping point.
Yeah. Basically a minimum level of contagiousness needed for something, a virus, a rumor, a product to actually take off and become an epidemic, or go viral. If it was below that threshold, it would just die out locally.
Okay, that sounds intuitive. Something needs to be infectious enough to spread widely.
But in scale-free networks, that epidemic threshold vanishes.
Vanishes completely. Why? Because of the hubs.
Even if a virus is actually quite weak, not very contagious on its own, as soon as it infects just one major hub, that hub instantly exposes it to potentially millions of other nodes.
Wow. So the hub acts like a super spreader regardless of how infectious the thing itself is.
Exactly. It bypasses the need for high intrinsic contagiousness. That's why even relatively weak computer viruses like the love bug around that same time could spread so devastatingly fast. Or why certain diseases can persist in populations even if they aren't easily transmitted between average individuals. The hubs keep them circulating.
That has huge implications for public health, for marketing, for information warfare.
Absolutely. Understanding the hubs is key to controlling diffusion.
And this isn't just abstract theory you mentioned earlier. This even applies inside our bodies, in our cells.
It does the network of metabolic reactions in a cell. It's scale-free. And it's also a small world. The average separation between any two molecules is only about 3 steps.
3 steps. That's incredibly close.
And the Achilles heel concept applies there too, with deadly consequences.
How so?
Well, think about genes and the proteins they code for. Some proteins are hubs in the cell's regulatory network connected to many other processes. Others are peripheral. If you get a mutation in a gene that codes for a minor weakly connected protein, the cell can usually cope its fatal less than 20% of the time statistically.
But if the mutation hits a hub gene,
Then it's often catastrophic. Take the p53 gene. Its protein is a major hub in controlling cell division and preventing cancer.
I've heard of p53, the guardian of the genome.
That's the 1A mutation that inactivates p53. It's legal to the cell's proper function 60 to 70% of the time. It's a direct route to cancer because that central control mechanism is broken. The cell's own network has critical vulnerabilities.
Wow. So cancer can be understood partly as an attack on a biological network hub?
That's a key insight from network biology.
Yes. Okay, so let's try and synthesize this. The huge takeaway from network science seems to be that the underlying structure of our connected world isn't random or uniform. It's this scale-free hierarchy dominated by hubs.
That's the core discovery. It's not a homogeneous web. It's a landscape with massive peaks and countless valleys.
And the peaks disproportionately shape how the whole thing behaves. And knowing this gives us a new lens to understand why complex systems sometimes fail spectacularly.
Right. Like the big 1996 power blackout in the western U.S., it wasn't just one power station failing, it was a cascading failure. An unexpected overload on one part of the grid due to its connections tripped neighboring parts, which tripped others. The interconnections, the network structure itself, allow the failure to spread catastrophically.
But it also helps explain massive successes, right?
Definitely. Think about the early days of Hotmail. How did it grow so fast?
It was free and every email had that little ad at the bottom?
Exactly. It essentially eliminated the adoption threshold. Didn't need to be intrinsically amazing, it just needed to infect the network. By making sign-up easy and turning every user into an advertiser, it leveraged the network's connections, hitting hubs and spreading exponentially. They tapped into the network dynamics perfectly, maybe without even fully realizing the theory behind it then.
So really understanding this network topology, the hubs, the vulnerabilities, the way things spread, it's not just academic anymore.
Not at all. It's become absolutely central for business strategy, for cybersecurity, for epidemiology, for designing resilient infrastructure. It's fundamental to navigating the modern world.
So if we've learned that the very structure of our networks dictates their fate, how vulnerable they are, how ideas or viruses spread through them, perhaps the final thought for everyone listening is this.
What's the critical, maybe hidden hub in your world?
Yeah, in your professional network, your personal life, your information sources. What's the linchpin holding things together? Or conversely, what's the single point of failure that could make your own system vulnerable? Something to think about.